Today we're going to look at some special products when we're factoring. And if we can recognize those special products just looking at our problem, it's going to make it a lot easier and a lot quicker to factor those. So we're going to really look at kind of three categories here. We're going to start with difference of squares. And these are all named very appropriately. When we say difference, we're talking about subtraction. When we say squares, we're talking about perfect squares. So some examples of perfect squares are like 9, 3 squared is 9, 49, 7 squared is 49, 100, 10 squared is 100, 25, 5 squared is 25. So anytime you see a problem where we have subtraction and our first term and our last term are perfect squares, these are really quick and nice to factor because we're just going to have a plus b, a minus b. Basically, the square root of a goes here, the square root of b goes here. One is going to be plus, one is going to be minus. So some examples of this. I'm going to go ahead and draw my factors here. I have x squared minus 16. We know that 16 is a perfect square. We know that x squared is a perfect square. Well, the square root of x squared is just x, so we start out with an x. The square root of 16 is 4, so I put a 4 here, 4 here. My rule says one of them is plus, one of them is minus. This is fully factored. So when we see the difference of squares, all we have to do is take the square root of each term, make one plus, one minus. Okay, same thing on 301. I'm going to draw my two binomial factors here. We notice that 9a squared is a perfect square. 25b squared is a perfect square. And it's difference. This is really important here. We'll see one that does not work later. So if we take the square root of 9a squared, we get 3a. We start both factors with 3a. If we take the square root of 25b squared, we have 5b. We know that one of them is going to be plus, one of them is going to be minus. And if we wanted to, we could multiply this back out and just make sure we get our original problem, but in this case we will. Okay, so on example 302 here, you might look at this and be tempted to say x plus 6, x minus 6, but if we check this, if we multiply this out, we get x squared minus 6x plus 6x minus 36. Well, these two give me 0. So we get x squared minus 36. Notice here our problem was x squared plus 36. So this is the sum of squares. And we actually cannot factor the sum of squares. This is just prime. So if it's not the difference of squares, we cannot factor it. So cannot factor, it's prime. On example 303, we have a to the 4th minus b to the 4th. So if we think about both of those, these may not look like perfect squares right off the bat, but we know that the square root of a to the 4th is a squared. So we have a squared, a squared. The square root of b to the 4th is b squared. We know one of them is going to be plus, one of them is going to be minus. But we actually don't stop here. If we look right here, we have the sum of two squares, which we just said cannot be factored. This is prime. So I'm going to keep that the same. But look here, we do have the difference of perfect squares again. We have a squared minus b squared. So this one actually can continue to be factored. We can factor it just like we have the ones above. The square root of a squared is a. The square root of b squared is b. One's going to be plus, one's going to be minus. So this has three binomial factors here. And then one more that's similar to that is x squared minus 16. Again, may not look initially like perfect squares, but it is. So if we take the square root of x to the 4th, we get x squared. If we take the square root of 16, we get 4. One's going to be plus, one's going to be minus. Again, we don't stop here. X squared plus 4 is the sum of squares, so we can't factor that anymore. but this one we can. This is the difference of squares like we saw before. We can factor that. The square root of x squared is x. The square root of 4 is 2. One's going to be plus, one's going to be minus. So for all of these, it is helpful to recognize your perfect squares. So you might just come up and make a list up here of your perfect squares. We have 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. That at least gives you the perfect squares between 1 squared and 10 squared. You can continue on if you want to, but those are the ones that you really should recognize as perfect squares, and we'll help you do these a little bit quicker. Okay, so we can also factor perfect square trinomials, which are trinomials that factor to be this right here. When you're factoring perfect square trinomials, you really can like just use your normal factoring of trinomials or factor by grouping, but it just makes it easier if you recognize that our first term is a perfect square, our last term is a perfect square, and that our middle term is 2 times a times b. Okay, so sometimes these are a little bit harder to recognize. Again, really what you're looking for, do you see a perfect square at the beginning? Do you see a perfect square at the end? And then we're going to see if our middle term is 2 times our a times b. And the way that this really factors into the same thing 2 times, like a plus b times a plus b, or a succinct way to write that is a plus b squared. So let me pretend, just on example 305, that we don't recognize this is a perfect square trinomial. We say, okay, we're just going to factor this like a normal trinomial. What multiplies to give me 9 adds to give me negative 6. Well, they're both going to start out with x, a negative 3, and a negative 3. Negative 3 times negative 3 is 9. Negative 3 plus negative 3 is negative 6. Well, we get this same thing 2 times. So we could rewrite this as x minus 3 to the second power. You could leave it like this, x minus 3 times x minus 3, or like this. Okay, or if we're working on this, we could recognize this is a perfect square, this is a perfect square, and this is 2 times our a times b. Okay, so same thing for example 306. I'm going to give my 2 binomials right here. This one especially is a little bit more complex than example 305. So we notice here 4x squared is a perfect square, 25y squared is a perfect square. So we are hoping, we're going to try to go ahead and factor this using that. We're going to say, okay, the square root of 4x squared is 2x. The square root of 25y squared is 5y. And because this is positive as well, we need this to be plus 5y plus 5y. Or we could write this as 2x plus 5y to the second power. And we could double check that. We could multiply it back out, make sure it works. We should get what we started with. Okay, and then the last types here are the sum and difference of cubes. These are kind of 2 rules, but they're really similar. So we're going to kind of lump them together. So when we talk about perfect cubes, I'm going to make a list here. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. And then I'm going to just put dot, 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 because honestly, I don't remember from there. I'd have to use a calculator. So you could continue your list just to recognize perfect cubes. When we are factoring perfect cubes, I'm going to show you how I learned it because I think this makes it easier. We're going to use what's called tap, tap, and then we're going to use SOP. Okay, let me explain what these random words mean. So when we recognize the difference of cubes, this right here is the difference of cubes. This is a perfect cube. This is a perfect cube. I'm going to set this up as a binomial times a trinomial. Okay? So from here, to fill in our binomial, we're going to do the cube root of this is m. The cube root of this is 3. All right, so to fill in our trinomial, I'm not going to put any signs. I'm not going to put any pluses or minuses right now. Okay, so I'm going to go, this is where this tap tap comes in. To fill in, we have 3 terms here. 1, 2, 3. I'm going to go tap tap. M times M is M squared. For the second one, I'm going to go tap tap. M times 3 is 3M. For the last one, I'm going to go tap tap. 3 times 3 is 9. Okay, so that's where this little tap tap comes in. And then here's where this SOP comes in. SOP stands for same, opposite, positive. This is what helps us come up with our signs here. Our first sign is going to be the same as our problem. The second sign is always going to be the opposite. The third sign is always going to be positive. So if you can remember this, this is true for the sum of cubes and difference of cubes. So basically, if you recognize cubes, we're going to use the tap tap method, same, opposite, positive to come up with our symbols. All right, let's try one where we have the sum of cubes here. 125p cubed is a perfect cube. 8r cubed is a perfect cube. So I'm going to write my binomial. I'm going to write my trinomial. And for my first binomial, I'm going to take the cube root of each. Cube root of the first one is 5p. Cube root of the second one is 2r. I'm going to leave my signs empty for now. So now to fill in these 3 terms, we're going to use our tap tap. So we're going to go tap tap, 5p times 5p is 25p squared. For the second one, we're going to go tap tap, 5p times 2r is 10pr. Our last one, we're going to go tap tap, 2r times 2r is 4r squared. All right, let's fill in our symbols here. Same, opposite, positive. We're going to do the same as our problem, the opposite of our problem, and then positive. So this is how we factor when we see the sum or difference of cubes. We do it just like this. All right, and then now let's kind of mix these things up here. So we're going to have, here's our rules. Difference of squares, sum of squares, we said we can't factor its prime. A perfect square trinomial, the sum and the difference of cubes. Okay, so our first one, let's just first try to recognize what's going on here. The first thing we do for any factoring problem is look for a greatest common factor, because at first glance, this doesn't look like any of those special products. But we do have a greatest factor of 2, so we can take a 2 out of each. And I'm left with 36x squared minus 1. Well, now if we look at this, we do have the difference of squares. So let's think how we factor the difference of squares. I'm going to leave my greatest common factor in front. Square root of 36x squared is 6x. Square root of 1 is 1. 1's going to be plus. 1's going to be minus. We are finished factoring this one. Okay, for the next example, again, it's kind of hard to tell what's going on here right now, so let's see if we can take out a greatest common factor. If we look at all 3 of our coefficients, we can take out a 3. If we look at all of our variables, we can take out a y. So if we divide each piece by a 3y, we're left with 16x squared minus 8x plus 1. Okay, if we look at what's left inside of here, again, if you don't recognize that this is a perfect square trinomial, that's okay. You could always factor this by grouping, and it's not too bad. But if we do recognize that this is a perfect square, this is a perfect square, we can factor this just like this above here. So the square root of the first one is 4x. The square root of the last one is 1. And we need our sign to be negative because we need those to add to give us negative 8. So we get 3y times 4x minus 1 squared. All right, and then one more right here. Again, hard to tell what's happening, so let's see if we can take out any greatest common factor. If we look at our coefficients, it looks like the only thing we can take out is a 2. If we look at our a's, we can take out an a to the first. If we look at our b's, we can take out a b squared. So if we divide each piece by 2ab squared, we should be left with 64a cubed plus 27b cubed. Well, now we're just looking at what's inside of here. Right here, we have the sum of cubes. So this is where we're going to use our tap tap. And then same opposite positive. So let's create our little binomial, our trinomial, and I'm going to leave that greatest common factor, tag it along out in front. Okay, the square root of my first one, the cube root of my first one is 4a. The cube root of this one is 3b. Let's use our tap tap to help us fill in our trinomial. Let's go tap tap. 4a times 4a is 16a squared. Tap tap. 4a times 3b is 12ab. Tap tap. 3b times 3b is 9b squared. Okay, let's use SOP, same opposite positive, to help us fill in our signs here. So I've got the same sign, which is plus, the opposite sign, and positive. So once we take out a greatest common factor, we can continue. And in this case, we had a sum of cubes left. Oh, and actually, we're not quite done here. If you look at this one, we have a perfect square trinomial again. Notice we have a perfect square right here. We have a perfect square right here. So if we continue, perfect square trinomial is going to factor to be something to the second power. The square root of 16a squared is 4a. Square root of 9b squared is 3b. And we need our symbol to be a minus. So let me bring down the rest of this. We should end up with this as our final factoring. So sometimes these have multiple steps for factoring. Sometimes after you factor it, you end up with another thing that you can factor. So you just continue until there's nothing else that you can factor.